Vadim.
Так. Окей, значит, Вадим Вологодский. Нет, все слова по отдельности понятны, а вместе нет. Арифметика, уравнение Knizhnik-Zamolodchikov.
Thank you very much. So I'm going to talk about joint work with Marchenko. Knizhnik-Zamolodchikov equation, well, I should confess that I do not understand these words either. It comes from representation theory, which I don't know much about, and also I think that my talk, representation theory, well, has very little to do with representation theory. It doesn't have any applications to the latter. So I will use so the algebras will not appear in my talk. I will use a kind of geometric construction of a very special case of Knizhnik-Zamolodchikov equation, and that is the following. So I take a.
Васька, тебя можно записывать?
Да. I will consider polynomial function f5, which is x minus c1, x minus c2, x minus cn. So this zi, the roots of this polynomial, well, these are points of the configuration space. So I have, I consider the subspace C of the affine space, n-dimensional affine space, given by, so it's open subset, given by inequality Zi is not equal to Zg. So this is spectrum of the following.
Sorry, will you consider any case when the ground field is different from C?
Yes, that's I'm going to exactly. So that's a good question. So in fact, for now, I'm just going to look at the affine space over the ring of integers. So I consider spectrum of the following algebra: Zi minus Zj. So this is the coordinate ring of this open subset of affine space by these inequalities. And so I think of phi as a rational function on the projective space over this configuration space E. So this is B1 Z. Now I will, well, this rational function phi gives rise to a local system. One-dimensional local system on this projective one times spec Z H. So what is your local system? So it's a trivial line one with a generator, and let's call this will be B1W. So W is the product. Of Z spec Z H inverse. And so this is a trivial local system on B1. Sorry, trivial line bundle. And the connection is given by the following formula. So it's a trivial line bundle, and this is just a symbol. It's generated by this symbol, and the connection is given by the following formula. So nabla of f times phi h. Well, it's just a differential. So it's phi h df plus h d phi over phi. Okay. Does it make sense? So of course this connection has singularities at certain points, namely, so here I have this projective line, I have divisor. So these are, let's see, conditions. These are going to be, well, there is a divisor to infinity where x is equal to infinity, and there is also divisor ci. And this is given by equation x equal to ci. This is, and also I have projective line w, corresponding divisors, it's just a product ci here. So this is a connection with logarithmic singularities at this limit. So t is I. So nabla is a map from structure the trivial bundle to logarithmic differential force. You want logarithmic singularities. Very good. There are any questions? So, I know.
What is Knizhnik-Zamolodchikov equation?
Yeah, so now Knizhnik-Zamolodchikov equation is, for me, it will be the following. I will take, here, so if I have a local system, well, I have a map from projective line to the configuration space. So each here is a parameter, right? Later we'll specify each. We specialize to the, well, we'll just specialize. We can specialize each to complex number or an element in a finite field or whatever, anything. So, but it's considered to be as a constant. And so this is a local system on P1 times the configuration space, which depends on a parameter H. That's how I want to think of this. And now what I can do, I take homology of the fibers of this projection, just homology of P1 with coefficients in this local system. So my the local system, the Knizhnik-Zamolodchikov local system that I'm going to study. Sometimes I will suppress this index H. Is just H1 Durand, logarithmic Durand homology of P1 W relative to W. These coefficients in this local system. So by definition, well, it's something very concrete. So you take force on P1, and So first you take functions, and of course every function on P1 is constant, so you get just functions on the base, and and then you take logarithmic differential forms. So with logarithmic singularities here. So how many logarithmic forms on P1 we have with singularity set n plus 1 points? So we have n-dimensional vector space of logarithmic differential forms. So let's introduce this notation. It's going to be eta I, and this is d x minus zi x minus zi. And so this is sum I equal 1 and gamma eta I. Okay? And the map takes f to h times f times sum of eta. So this is a complex that computes logarithmic rank homology, and I take its homology integral 1. So this is a quotient of n-dimensional vector space spanned by this eta by single relation that the sum of this eta is 0, right? So this is well, as a vector bundle on W again, it's trivial, so it's not very interesting. But what is interesting is a connection. So this comes together with a Gauss-Manning connection that I will denote by now, and this is the Gauss-Manning connection. Whenever you have a family of manifolds, varieties over space, you have a local system defined on the total space, the relative homology of the fibers form a local system over on the case. So. Very good. Are there any questions? So that's the local system, n-1 dimensional local system that I'm going to study. So so again we can classical theory.
This is the KZ equation.
That's a very special case of KZ equation that associate to the group the algebra SL2. That's the powers of standard KZ.
And where is SL2 here?
Well,
So it's kind of n points on sphere in normal KZ language, yeah, but where is SL2? Where are matrices 2 times 2?
well, so I will write down an explicit formula for the connection. Maybe it's still, I mean,
В точке ставим представление, там еще какой-то вес берется. Теперь представление все двумерные, во всех этих точках, Z1 и так далее, Z.
А где вот здесь было сказано, что они двумерные?
Не, это так получается.
So I will write down an explicit matrix for this connection. And it turns out that this is, well, it's a direct sum in KZ connection associated to SL2 and standard. So it's not okay. So so how to compute this connection explicitly, right? So well, I will write. I will give you a formula. formula and I'll explain a proof which is going to be wrong. But easy to explain. And then I will explain how to correct. So so explicit formula is formula for connection. Okay, so let's do it by definition. So I have vector fields d over dzi, and I have a maybe not a basis but a system of generators, right? My E is generated by eta I, and there is only a single relation that the sum is C. Right? So and that's sorry, J here, and I will compute the covariant derivative of this. Okay. So how you do? What you do? You just take so there is in this formula there is a hidden symbol phi h, right? The connection is the Garris-Manning connection comes from the connection on this local system on the total space. So what you're supposed to do, you have to take by definition, you take the Lie derivative, you compute the covariant derivative, the Lie derivative of the form eta multiplied by phi to the h divided by phi. That's how in my notation, that's how you compute.
В одном месте G,
So you just well, you think of this as a kind of a function depending on the parameter h. This is a differential form. You take its Lie derivative, and then you can write it actually as a product of this function times a differential form. So okay, so this can be easily computed. This is negative h d of x minus y over x minus y x minus zg. And if I is not equal to j, I is not equal to j, then this is the same as h eta j minus eta I over z minus j. Okay, so that's we are almost so I explained how you differentiate classes eta I, where I is not j. But because sum of eta I over all I is 0, that's that determines this formula determines the connection here, right? So there is a kind of a flaw in this argument, and the flaw is that in fact this vector field, this Lie derivative with respect to this vector field does not act on the complex, because this vector field, right? So you have a what is the picture? You have your configuration space Z, and then you have P1, and then you have some divisors where you take the logarithmic singularities, and divisors look like this, right? And so now we start with a vector field here, d over dzi, and then we lift it that unfortunately this sleeve does not preserve the divisor, so the B derivative does not carry logarithmic differential forms to itself, so it's really a problem. And in fact, you see what the problem is. So if I is equal to j, then when you do the computation here, right, you get a form that has all of it, which is not right. The same formula, I is equal to j, but now it has the oh, there. So this is not good. But well, you can correct the one can nevertheless this formula is true, and one way to prove it is yeah. So definition of the Gauss-Manin connection is that you start with a vector field, you try to lift it to a vector field that preserves this this divisor, right? This cannot be done globally, but you can do it locally, and then you use Cartan homotopy formula to actually construct a connection on the logarithmic program homology. So it requires some work. But here is a cheap trick that allows one to, well, we can, so we have logarithmic program homology, of P1W over W with coefficients in this local system. But so instead of looking at forms with poles of order 1, you can consider poles with arbitrary of this poles of arbitrary order at divisor T, right? So you can just take usual cohomology, the round cohomology of P1W minus T over yeah, and so when you specialize H, say to an integer, there is a difference, right? There is a in general we have a restriction net, right? So we can embed logarithmic forms to all forms with to forms with arbitrary singularities at T. In general, this is not an isomorphism, but it is an isomorphism if you specialize H to a very general complex number. So is an isomorphism for generic. And that's enough, because at the end, the connection is given by certain universal metrics whose coefficients must be rational functions or even Laurent polynomials in H. So if you can check that it's given by a certain formula for generic H's. Okay, so I will write down the result of this computation as a matrix, and the matrix is going to be the following. So let's introduce matrix omega ij. It's n times n matrix with coefficients in integers and omega ij. So it has only 4 non-trivial entries. It's k, l, and Cii equal to Cjj equal to Cij negative Cji, negative, and it's 1, and all other entries, it's 0. And now the formula for the connection is the following. It's A. So the matrix is sum over all I and J less or equal than n. And you take omega ij over zi minus cg and multiply it by this. So that's a matrix of platforms on the configuration space. And it has a following property that its differential is 0, which is clear. Well, you have to use this formula. And also it has a property that A is also 0. So in particular, this A satisfies the Mayer-Cartan equation, but not only it satisfies A itself satisfies the Mayer-Cartan equation. In fact, it follows that if I consider
Кто у нас автор этой немецкой системы? А? Рослый? Засланный. Все
Okay, so yeah, so now you can use this matrix A to define a connection again on the trivial bundle of rank 1. Yeah. So I take the trivial rank and vector bundle, and the connection is given by D plus HE. And this formula, these two formulas together imply that this H times A also satisfies the Mayer-Cartan equation, right?
Это просто вот на первых гомологиях, да, соответствующие связаны?
Да.
Просто в одной явной.
Да, я даже еще не объяснил, как это вычислить.
То, что повторяет Mayer-Cartan, это априори понятно, да?
No, this is well, yeah. Right. Strictly speaking, the first homology is the quotient of this by rank 1 subbundle, and 1 goes to sum of yeah. So it's the fact that it's at least if you believe that the connection on E is given by this formula, then the flatness of the connection would imply that this A satisfies the Mayer-Cartan equation up to this quotient. But in fact, it's written here, and this is almost a split sequence of local systems. Namely, you can there is also a map to gamma, and right, you take just some of the coefficients, and the composition is multiplication by I, and so if n is invertible, it's p. And this map is also. Very good. So that's an explicit formula. And so what I'm going to do to this is, yeah, maybe just one property that I want to mention here is that there is a well, this matrix A is symmetric by construction. So it means that if you dualize H, then well, I want to say that you'll get H minus H. This is again not completely true because it's true that if you dualize this term in the middle, then indeed you get the same connection, but with with H replaced by minus H. But because it's in general, for if n is not invertible, it doesn't split, well, so what is true is that if you invert it, then it's so this is a corollary, but it has a more conceptual. This dualism has a more conceptual interpretation as a logarithmic point corrector. Okay. So now what I'm going to do
sorry,
is
I missed some. When you define this matrix A, how you sum over A, I, and J? Because you divide it by Zi minus Zj. Are the terms with I equal to J or not?
no. Thank you very much. Thank you. Okay. Very good. So what I'm going to do? Yeah. I'm not sure that I understand the question. Maybe it's, yeah, I mean, so this matrix is symmetric, and I take sum over all pairs, right? J here is not supposed to be larger than I. So you can rewrite it. So what I'm going to do with this, I'm going to specialize H to a monoid in, well, I could specialize it to a complex number, then I would get a local system over the configuration space, so a representation of the braid group, and they could study this representation, or, and that's what I'm going to do, I'm going to specialize H to an element in a field or maybe a ring which is like Z mod PZ, or maybe an algebraic closure of a finite field, or maybe something like Z mod and Z. And I want to look at, so take sort of the reduction of this local system model of P and look at arithmetic properties of this connection. And so let's P be a prime number. So here is the first field number. And I will assume that P does not divide M. And I take fix an invertible element in some field of characteristic P, say in Fp bar. So in other words, I fix this homomorphism. So H goes to some element H bar, which is non-zero, and then so I will take consider this local system, and I specialize to finite field. That means that I take E, H, and I tensor it over Z H inverse with F P. Right? So that's something very explicit. So I have a connection given by an explicit matrix, and I just plug in this matrix H equal to whatever element you like. For example, square root of 2. Yes?
А вот на C просто известно, что там за модулирование, что за представление?
Misha, maybe you can it is known, but maybe Misha, maybe you can describe this one. Representation of the braid group corresponding to this connection.
Скорее всего, плюрал.
What?
Плюрал.
Ну, я
Ну, в общем,
ни о чем не говорить.
Ну, который, ну, группа КОС отображается, ну, во-первых, нужно продолжить до
Descent to the closure configuration group by itself.
Да, так что
Configuration space by itself. Another.
Сказать, да.
So it's symmetric with respect to the
Перестановка, и тогда данная группа станет именно группой КОС, а не группой крашенных КОС. Тогда она отображается на симметрическую группу, у которой есть такое обычное перестановочное представление, минус намеренное. Называется reflection. Но оно деформируется до представления алгебры Гекке, ну, которая тоже является фактором групповой алгебры группы КОС. Вот это оно и есть.
But why do you want to descend it first? I mean, you can afterwards you restrict it to the group algebra of the group of colored braids, right? Pure braids.
Yes.
But is it just because?
But the pure braids have some complicated generators and relations.
I see.
And you cannot.
I see. So it's easier to describe if you first observe that this representation extends to representations of larger, slightly larger. Okay.
То есть в случае, если у нас было несколько H-типов для каждого из них, такие представления писаются.
Maybe I'm not sure. H-типов.
Такого раньше в мире не было.
А то есть мы на одну H умножаем уровень?
Игорь, а почему вы хотите ашиты разные?
But what people sometimes do, they sort of consider.
Если бы там была система корней не типа А, если бы Б, там были две разных длины, для этих длин были разные H.
you can sort of replace polynomial phi by
С группой V там не надо дальше.
H это K плюс 2.
Да.
Как вы сделаете разными, да?
Я просто правильно думал, как про внешнюю размер. Ну, в смысле, ну вот, порождающий x минус аид, x минус z, это степень аида. Свой аид для своего. Ну, для своей точки. И локальную систему тоже можно сделать.
То есть это то, что можно написать представление, да, на каком другом языке, вот, там известный термин, можно сформулировать, что получится такое.
С одним машиной. А как вот сами, с одним машиной, вы понимаете, какой это Knizhnik-Zamolodchikov? Ты что-то говорил про 2n минус 2.
Ну, n, скорее, n минус 2. То есть старший вес, ну, берешь тазовое произведение n копий двумерного представления, старший вес n. И вычитаешь один простой корень, это n минус 2.
Ну, я этого не вижу, но поверь.
Okay, so so here is the theorem, first theorem. So it turns out that so I'm going to study this local system. It turns out that this behavior it behaves completely different. Well, its behavior is in the case when this h bar is an element of fp is very special. So for example, you can take if you have a local system, you can consider flat sections. And it turns out that there are no flat sections unless h bar is f. Which is also the case, I think, for over complex numbers. If h is not an integer, then the representation of this spread group is reducible. Okay, and if h is in fp, and say, well, so it's let's if h tilde is its representative, so h tilde is equal to h bar of p. Then we can compute the number of flat sections, well, it will be more convenient for me to consider flat sections of the dual bundle, which is the same thing thanks to this duality. Well, it's not the same, but it's equivalent problem. I claim that this is so what flat sections form? In characteristic P, I have many functions whose differential is zero identity. For example, z to the fifth power, z1 to the fifth power, or z2 to the fifth power. So flat sections form a module over fifth powers. Okay, so and I claim that this is a free module over over fifth powers of rank n h tilde over. So you take this number, which is from 0, 1 to p minus 1, you multiply it by n, you divide by p, take the integral. So that's a number of from 1 to n minus 1. And that's the number of solutions. And here's how you construct the solutions.
These are sets over what?
Yes. Okay. So.
А это целая часть написана там, да?
Да.
Ага. А на цель, следует потому, что если h целое, да, то тоже есть какие-то плоские сечения. Как получается?
На C?
Да, да.
Да, очень смешно. Там они всем влияют. Сейчас.
Реально прямо?
No, well, sorry. It's not. No, of course it's topological counterparts, but this one is not. So other are flat sections. There are some flat sections. Yes, but.
For arbitrary H. Для любых ты сейчас говоришь или для...
Нет, для произвольных, для общего комплексного H никаких плоских сечений нет, соответствующее представление группы cos не приводимо. So if H is integral, then it's kind of strange. So this local system phi to H is trivial, but it's non-trivial as a logarithmic local system, right? So you can compute. I think that there are some. There could be some flat sections, but very few. If H is an integer, but viewed as a complex number. Okay, so here is what you do in characteristic bit, how you construct sections. You just take, so I want to produce a flat map, right, from E H bar to gamma Z or Z. P. And which is flat, compatible with the connection. And what you, well, this has generators, right? Classes eta I. And what you do is the following: you take eta I, and you
Actually, is it a proof of your theorem?
No, it's construction. It's construction of a. So I said that it's a free module. I will just produce for you generators of this module. So the proof is. I might describe it. Well, it depends on the audience. So at the very end, it uses some algebraic geometry in characteristic. So I want to concentrate maybe more on another theorem, which has more practical applications because it allows one to compute equations, approximation. Okay. So but then is how you construct that maps? It's very simple. So you. This is a trivial local system. So if H is integer, right? p to the h is actually a function. So think of this as a rational differential form. So so this is kind of dx over x minus zi times this function, so h is greater equal than 1. So it's not. In fact, it's a polynomial function, right? Because
Who is p?
yeah, it's phi is
This
x
polynomial.
minus z1 x minus z, right? So if I take phi to the h tilde over x minus zi, this is actually a polynomial, and therefore I can write it as a dx times x t times some coefficients d of z. And you can compute the degree of this polynomial, and you'll see that the summation goes from 0 to n h tilde minus 1. And so the solutions, the flat sections, are defined by the following form. You take, you send eta to C all p minus 1 from I equals. So you look at this polynomial in powers of x, and you look only at coefficients at of this coefficient. So you look at coefficients at x all p minus 1. So a very special case, a very special property of this differential form in characteristic P is that it's not exact. You cannot obtain this differential form as a differential of something. So, and that's why it works. So what, for example, so I claim that this is indeed a flat section, and first of all, I need to show that it's well defined.
Извините, пожалуйста, а вот что написано CDI от Z, что такое Z?
Точки затытые, набор.
А, затытое это?
Да, ну да.
Но это же полином по x и затытым.
А, вот так.
Okay? Does it make sense? So for example, I need to check that if I apply it to sum of eta I, then the result is 0, and this is the coefficient. It's p minus 1 of the h tilde x. This is derivative, and this coefficient, as I explained, if you take any function and take its derivative,
Fine, yeah?
phi, theta. And if you take any function and take its derivative, then all the coefficients at this powers of x are all equal to 0. So you get them. Okay. So this I claim that this, so the theorem, the more precise assertion is that this EIL form a basis in the space of assertions. Okay, so again, I might discuss proof of this, probably not. I should say that it uses, you can...
It forms a base as L goes from 1 to this integral part?
Yeah, because there is as many coefficients. Yeah. as many coefficients as this number. So d goes from here to here, so you'll have precisely this number of coefficients. So you can, okay, so now I want to describe structure of this local system when h is not an infinite. And that's, I think it's more interesting. In this case, there are no solutions, but still then you can, it has a very simple geometric description that I know, which is motivated by the steepest descent method that I will go into explain. And it's, I learned this from Roma in slightly different context. So, over complex numbers, suppose, so I have a differential equation that depends on the parameter h. And I can study asymptotic of solutions, local solutions to this differential equation when h goes to infinity. So this asymptotic is related to study asymptotic of integrals phi h as a function dx when h goes to infinity, and you can replace phi h by exponential of h log phi, and use the steepest descent method that localizes the asymptotic of these integrals at the critical point. And that's what I'm going to do. And it turns out that this method is very useful when you work in characteristic P or even over the integers. And that's kind of the main message of my So I will, there will be no integrals, but kind of the formulas that are precisely the coefficients of the asymptotic expansion and steepest descent. Okay, so here is here's what I'm going to do. Let's go back to a very general picture. So not in characteristic P over integers. So I have E. H, not H bar, so I do not specialize. It's H is still a parameter on the punctured line, and I want to. So again, this is all a module over over functions on z. That's this z join h and h inverse. And first, I want to extend this local system to infinity. So I want to allow h to be infinity. Yeah, so how you do this? Kind of the connection was given by explicit formula. So it was a EH was a quotient of trivial rank n vector bundle with a connection given by the formula t plus h times t. So when h goes to infinity, it has a pole, but I can get rid of this pole by multiplying by h. So then what I get is not a connection, but it's H inverse connection. It means that I don't have action of all vector fields. I have only action of H inverse times t. So it's the subalgebra of the algebra of differential operators generated by functions. So that's what I'm going to do. So and it also has a so first I will define. I could construct this extension geometrically. So first I define local system phi h. It's going to be again. It's a trivial rank one local vector bundle, but now over spec z actually h inverse, so it can be 0 h inverse. That's correct, and the connection number is it should be h inverse because it's not a connection. It's H inverse connection. So it's given by the formula H inverse d plus d phi over phi. Okay. So again, so if you think of a connection as action of differential operators, then this H inverse connection is an action of subalgebra of the ring of differential operators generated by functions and by H inverse tensor functions. So very good, and then I can extend my my local system, this Knizhnik-Zamolodchikov local system, to infinity. So I can take the logarithmic H inverse Durand homology. Durand homology is related to D modules, and this H inverse Durand homology is related to the subalgebra of differential operators. Logarithm of D1 Z spec okay. These coefficients in this H local system. So at the end, you'll get a local system on Z times their phi 1, and it's equipped with an H inverse connection given by this formula, the same formula. You just regularize it. Why it's convenient for me now? I will. So my goal will be to describe this object in a formal neighborhood of when H inverse is very close to 0. In the formal neighborhood of 0. Original coordinates, formal neighborhood. Okay? So, and here is the description. So the description is related to critical points of function phi of this polynomial.
points.
Вот, да. И он по этому хочет маленькое.
So here's what you do. You take inside P1, and in fact even inside A1, you consider closed subspace given by one equation, phi prime x equal 0. So this is just derivative, partial derivative with respect to x variable, and so it starts as xn minus 1 plus something. So there is a map from here to z, and if you invert them, it's going to be finite of degree n minus 1, and over, I can look at the open subset here, open, where this map is unramified, where where this polynomial, it consists of this subset consists of all tuples of z1, z2, zn, such that this polynomial has no multiple roots. So this is a finite. A tau means that it's unramified color. And finite means that the fiber consists of n minus 1 points over any. So let's give a name to this. Let's call it nu. And explicitly, it's given by this z0 is given by one inequality that the discriminant of this polynomial is not. So it's the complement, right? It's just so this critical locus, well, it's by its notation suggests it consists of critical points of phi, and here the critical points are not degenerate. These are Morse critical points. Yeah. So the derivative is 0, but the second derivative is 0. And therefore you have the Hessian. Well, if you have a manifold and a point, a function, and a critical point, then when derivative is 0, then Hessian is a symmetric bilinear form on the tangent space, right? So, and the point is the critical point is a Morse point if and only if this Hessian is not degenerate. And if it's not degenerate, then it also defines a symmetric bilinear form on the dual space. And this is a I can think of this. So my dual space, well, is, I have one coordinate only, so one-dimensional situation. So the tangent space is actually one-dimensional. So this is so the Hessian is a. I can think of this simply as a trivialization of this line. Okay. Well, explicitly, how it works. So dx, tensor dx goes to 2 over second derivative. Yeah. And so this trivialization. Well, notice that when I look at the 0, so the 0 number integer n is already invertible, right? So it's if n is if we specialize divisor of n, this is not a finite power of degree n minus 1, and also 2 is invertible. 2 is invertible, and therefore a trivialization of this tensor square of a line bundle gives me a connection on this line bundle. So connection. One. So if you have the normal bundle to the critical locus comes with a canonical connection. If all the critical points are Morse critical points. So I will write down a formula for this connection just to convince you that it's not something very complicated. So if you have a line bundle, given a line bundle with a realization of its tensor square, it's the same thing as a given twofold cover of your space with a realization of your line bundle over this cover, and so in particular, yeah, this is a geometric construction of the connection. I'll give you for this. So the connection is that number of dx is negative 1/2 of d log phi double, right? Then dx. Okay, and now we can formulate the result. And there will be two results. One is make sense over complex numbers, which is very weak and boring. And it turns out, however, that when you reduce model of some integer, it becomes much more interesting. So the result is the following. So let's consider the critical locus. So it has map to Z0, and I denote it by mu. And let's multiply it by spec Z H inverse. So here, okay, so, and now, so this critical locus I have a one-dimensional local system. This one-dimensional local system is will be phi to the h, restricted to the critical values. Tensor out with omega 1 b1 z z also restricted to the critical values. So that's a local system, and I want to view it. And this is a finite entire map, right? If I have a local system here, I can think of this as global sections form a local system. Well, this is here I have a rank n, rank 1 local system. When I take its direct image, when I view it as a local system, it has rank n minus 1. So this is an entity. Okay. So I produced for you a local system here. It has the same rank as the Knizhnik-Zamolodchikov local system, right? And it's defined not on over the whole configuration space. It's defined only on some open subset, right, where the discriminant is not zero. And so let's see what the claim is that it's related to the Knizhnik-Zamolodchikov to this E. Okay. Good. Theorem. Okay, so the boring theorem is that when you take this Knizhnik-Zamolodchikov guy and restrict it to the formal neighborhood, so you take spec of z double brackets h. So this is a formal power series. So when you restrict it here, you can't really get any like topological information about E. You can specialize like h inverse equal to something. It's just formal power series. But then, nevertheless, it's a local system here with an H inverse connection, and as such, it's isomorphic to L. This difference. And now the second statement is that if you reduce it modulo an integer, well, by Chinese remainder theorem, you may, I'm going to reduce it modulo power of a prime number. So it's by Chinese remainder theorem. This is good enough. So I fix some prime number which is not divide to a. And in fact, otherwise the reduction would be zero. And I take this E bar and I restrict it to 0. So here I take spec z mod p to the mz. Right?
M is arbitrary.
M is arbitrary, right? And instead of looking at the power series at H inverse, I just look at the rational functions with very simple rational functions. Will be H inverse, the power p minus 1, minus 1, and this. Right? So you just you consider polynomials in H inverse, and you invert one polynomial. So you remove from the line points where H inverse is an element of zeros of this guy. Yeah. So if n is 1, it means that I just remove p minus 1 points where H inverse is an element of fp star. Okay, and then it's the claim is that this is it's still this asymptotic formula remains an exact formula when you boils down to an exact formula for when you reduce mod p to n. So you stick to this. Okay. So,
Но в комплексном случае асимптотической.
в комплексном случае асимптотическое, оно не имеет никакого отношения к решению. То есть, ну так бывает, что повезет, можно там как-то так контур сместить и изучать асимптотику. Но в общем это просто это не настоящее решение. Вот в характеристике по модулю P степени это настоящее. I will just, I think I have to, maybe I will illustrate this in one example, which is in fact a general. Well, everything is reduced to this very simple example. So I want to illustrate, explain A and B in the simplest possible case, when my function phi is part A tells me that this says that this everything depends on phi in a neighborhood of the critical locus. So in a neighborhood of a critical locus, a Morse function can be written as a constant plus a square.
Да, то есть хотел сказать, что фи просто квадратичный.
That's so I want to consider illustrated in the case when phi is a quadratic in one variable. It's very simple. So let's see what's going on in this case. So it all boils down to some very concrete computation in this beta functions. Okay. So I take for phi 1 plus x, and I take some ring R, arbitrary. In applications, it will be some like maybe functions on the critical locus. So functions on the crit 0, but it can be any ring. And I consider the following complex R so I have consider neighborhood of the critical point. Critical point is x equals 0. And the differential here is going to be h inverse d plus d phi over phi, which is 2x over x squared plus 1.
А вот что открываются две скобки, открывается одна.
Yeah. Thank you. No good. No good. So and then it's x h inverse dx. But I'm interested in homology of this complex. Well, homology is easy to see that it's something here, the co-kernel. And so I claim that there is a map from here to here, which induces an isomorphism on the homology. That's immediate. Well, the map just takes 1 to 1. To dx. And the fact that it induces a quasi-isomorphism homology it's very simple, since everything is complete with respect to h adic topology, h inverse adic topology. It suffices to check that this is a quasi-isomorphism modulo h, and then you just look at this formula. So this term goes away, so you have the differential simply multiplication by 2x. So it's really quasi-isomorphism. So this is the homology of this complex is only in degree 1, and this is this. Now let's try to construct the inverse. The inverse. And let's try to derive. So if it's so the inverse will be the map from the co-kernel of this map to this guy.
Где важно, что там 2х поделить на 1 плюс x квадрат?
Это важно только, что если бы здесь было бы x в квадрате, было бы очень плохо. Важно, что это морсовская критическая точка. Больше ничего. Okay, so and then it will be, though it will be important in a second. For now it's not. But it will be important. Right. So let's try to, well, since it's an isomorphism, we should have the inverse map from homology of this complex to this guy. And it's characterized by two properties, that A of 1 is 1, f of 1 plus dx is 1, and A of f prime h is plus 2x over x squared plus 1 times f is 0. And okay, so let's using these two formulas we can compute a of x. I'll do this. So let's take this formula and let's plot here f equal to x k minus 1 plus x k. And then so rewrite. So this identity is equivalent to the following recurrence relation, that a of x to the k power
Times
is
dx.
for say
Times dx.
times dx, right? Times dx is equal to minus a of x minus k minus 2. That's one. So yeah, so that's a recurrence relation. So what you see is that a of x k dx from here is is 0 if k is odd. And to compute it for n k, you use this recurrence relation and the fact that a of 1 dx is 1. So here is the formula that you get. So I'm computing for you the integral of this expression 1 plus h squared to the h power times h to the k. So this integral is given by this, computed by this recurrence relation. And the formula that you have is that a of y to k is equal to minus 1.
Why is it y?
Oh, it's x dx. Minus 1 to the n to the k. Lambda h minus k times the following 2 k minus 1. So it's product over all odd numbers, 2k minus 3, 1, over h inverse 2k plus 1 plus 3h inverse plus. Okay, so what you see from here is that here you have the product of all odd numbers. So when k is large enough, this is just 0. So that means that in if you work modulo power of p, this map A takes polynomial differential forms to actually rational functions in H inverse. And what do you have in denominators? Well, you see you have denominator. Well, if you multiply it by a power of this polynomial, you get rid of this. So it's not only a rational function, it has a very special form, right? So there are two situations. Either this is invertible in this ring, and then this is a polynomial in H inverse with integer. This are kind of, well, this are going to be, so if this is non-invertible, then, then it's nilpotent, right? It means that 1 over this guy is actually a polynomial in H inverse, right? Because if you have H inverse P plus 2, this is definitely a polynomial in H inverse, if P is nilpotent. Otherwise, you can multiply this guy by the power of this guy, of this polynomial, to get rid of the delineators completely. So this way, this shows that this map A actually, so if P to the M R is 0, then it defines a map from merely from polynomials H to R of H inverse and H inverse minus 1. And you can also, after localizing it further, after inverting this number, this is actually a cross matrix. Okay? So when you work modular power of M, so this kind of formal isomorphism becomes a true isomorphism. And then you localize at the critical point that you get that. That's probably all I want to say.
Спасибо. Further questions? Вопросы? Те, кто знает, что такое уравнение Knizhnika-Zamolodchikov. Ладно, спасибо еще раз. Сейчас, кстати. Максим, ты что-то спрашиваешь или что-то утверждаешь? Хорошо.
Спасибо.
А все-таки что это для критического уровня? Это что-то означает или еще не означает?